Hello, it's a talk of Serge Guelton. He's developer of Pythran, and the talk is surviving in an open source niche, the Pythran case.
Thanks. So we are back to a more intimate area, human scale, not like the one before. So I'm going to spend the next 50 minutes speaking about a project I developed. It's nothing at the scale of Python 3 or whatever. There may be less users of this project than the number of people in this room, but that may change in the future. And anyway, I think that the idea I want to share are beneficial, even if you don't use the software. So a few words about me. So I'm basically a research engineer in a security firm where I do compilation stuff. I'm also a associate researcher in a French university, a developer of the project I'm going to present to you, and an LLVM committer. So what is Pythran? Pythran is a compiler, a static compiler, no just-in-time compilation, basic compiler, just like you would use GCC for C or C++. You can use Pythran for Python code, but not for any Python code. It's for scientific kernels, okay? So only for the scientific word. And the input is not plain Python. Well, it is, but it's a subset, a strict subset. So there is no extension or whatever. Every code that compiles with Pythran is also a valid Python code, but not in the other way. So basically you write your scientific kernels. You had a few comments. So as there are comments, they can be ignored or whatever, and the Python code still runs. But the Python compiler understands these comments and use them to generate native code. The comments are not meant to be intrusive. There's only a few comments for function declaration, nothing at the variable declaration level or no extension or whatever. Just state which function you want to export, and they will be this module will be compiled as a native module, and only this function will be available in this module for this particular signature. So here I have a Rosenbrock function. I don't know what is it. But I can write it in NumPy, and I can export it stating that it accepts an array of integer or an array of double precision floating points. So why is it a niche? It's a niche because scientific computing is a niche. Well, there is a quite big community in scientific computing and Python, mostly due to the NumPy, SciPy, Jupyter, and Matplotlib stack. And when the Python performance are not enough, there is also a wide range of choice to optimize your code, ranging from Cyphons that will be presented in the next talk, to NumX, Pro, NumBar, and a few others. And there is also a lot of things happening, or that are trying to happen in the world of compilation and Python. There are some very long-term projects like PyPy, Cyphon, or JFON, and some recent projects like NumBar or Hope, and a lot of that project, which is an hint about the difficulty of the task. Copperhead to generate GPU code, Piston from Dropbox, Aladdin Swallow, Parakeet, and all those projects are now dead, but they tried some ideas to compile some kind of Python code. The ideas in the air when you want to compile Python codes. Say, okay, well, it's easy, I just add types to every function declaration, so I don't have any lazy binding or dynamic dispatch. Everything will be static, and then I translate that to C++, choose your poison, it doesn't matter, as long as it's a statically compiled language. And I make a lot of assumptions about the imported module. I don't care about how Python actually imports module. I use import just like I would use jsinclude or thing like that, and I stick to a subset of the language which is easy to compile. And it's relatively easy to make that work. But you can also do some more advanced stuff. So that's just translation. Translation is not compilation. Translation is what cat does or sed does. Compilation transforms the code. So you can take all the compiler knowledge that exists since the 50s and put it into compiling Python. There are some specificities in the language that make it an interesting target. You can use just-in-time compilation instead of ahead-of-time compilation, and you can try to support a larger subset of the language, support generator, or support class, meta class, or what you want. And if you're really very bold, you can try to be ready to be compatible with whatever Python code exists. Only bytecode, but any bytecode. That includes supporting the import mechanism, lazy binding, on this kind of stuff. That's what PyPy is doing. And you can also try to be compatible or to optimize native extensions. And optimizing native extension is a big deal. It's very important, especially in the scientific world, because people tend to use Python as a glue and to write kernels in native code, and then they want to optimize cross-native codes. Pythran is somewhere in the advanced area. It's definitively not in the expert area, and most of the basic stuff has been done. So it's an open source software. BSD started 6 years ago. You can find it on PyPy, on the cheese shop, on Conda, or on GitHub, depending on your the way you want to use it. There are some Python dependencies, NetworkX to do some graph compiler algorithm, NumPy for all the scientific stuff, PLI, which is Lexiac in Python for the sub-language we use in the export line, and GAST. I'm going to speak about that. Victor told us that moving from Python 2 to Python 3 is a matter of syntax. But when your input is Python, moving from Python 2 to Python 3 means changing the input of your program, like changing the SQL schema or things like that. So it was actually a very difficult thing for us to move from Python 2 to Python 3. It was not just adding parentheses around prints. It was changing the inputs. And when you meet the range built in as an input, it creates a list, or it creates a generator. So it's different stuff, so you need to compile them differently. So that was a difficult step, and we introduced a thin layer to abstract the Python AST in that, so that's generic AST. And you also need, and that used to be a very difficult step, you need a C++ compliant, a C++11 compiler, and back in the day, it was not the case. It's actually still difficult to find a compiler that handles every C++11 constructs. Even on Linux with Clang or GCC, there are still some stuff that are not well handled. And when you start to switch to Windows, then things start to be very difficult to support. But it's getting better, because Ubuntu now ships a decent version of GCC, so most people have a decent compiler, and well, that's no longer a source of issues on GitHub. The community is quite small, so the buzz factor is of 1, me, but I do receive a few contributions, sometimes from students of mine, so it's not really a choice, but they do enjoy their contribution, and sometimes from foreigners. So that's something I really appreciate, because I'm not trying to grab a lot of attention more than having fun technically and provide things that can be interesting for people as users. But sometimes users do submit a pull request. Sometimes it's just to fix a typo in the README, and sometimes they do implement stuff. So that's still great. Behind this compiler, there are 3 ideas that make it quite different from other Python compilers. The first idea is that there is no mixed mode, where Python code calling, or C code calling the Python C API lives within pure C code and everything works together. That's the Python approach. And our approach is either you can compile to pure native code, and there is no call to the Python C API apart from the frontier, or you can't compile. So that may look like a very harsh choice, but there's a lot of nice things. First, as there is no longer any Python C API call, you can release a GIL. So you can make multi-threaded calls to the Python generated modules, and release the GIL, and that works. So that's a nice point. The other point is that as you generate Python free code, you could generate a module, a native module that can be imported from Julia or from Rust. That's not implemented, but that's something that would work. You could prototype your code in Python and then import it from Julia or Rust. That's something I want to try this year. The other point is typing. Writing a good type inference algorithm is difficult, so either you have to read a lot of bibliography, which is in itself difficult, or you have to try to reinvent the wheel, and then realize that there is a lot of literature, but that's not for nothing. Or you say, okay, duck typing, it's really similar to template, C++ template instantiation. In fact, C++ template use static polymorphism, and duck typing provides dynamic polymorphism, but in a static word, it's enough. There is a match between the two. So basically, we generate C++, and it happens to be correctly typed. We don't try to infer the type of, we just generate meta programs, C++ meta programs, and we instantiate them for several types, and native code gets generated. That sounds magic, but it actually works. So the typing code in Pythran is not brain-damaging, and that's cool for me, because that's not my expertise area. And the next idea is we don't generate low-level code. If there is no loop in the original code, we don't try to generate loop in the final code. We basically rewrote the Python built-ins, part of NumPy, random module, iter tools in C++ in a full template and generic way, and we generate code to this high-level C++ library. The good thing is that if you want to increase the library support, you just have to write a bunch of decent C++ code. Well, for some definition of decent, but still, it's feasible. Another good thing is that as we keep the source-to-source translation at a high level, if you put, we added this feature, if you put OpenMP annotations on your Python code, then they can be translated to C++, and they still have the correct meaning. The semantic is respected, and we actually support the full most of OpenMP free language from Python. And you have your multi-threaded code that runs on multiple cores. So that sounds like a lot of stuff, but there's not that much code. So some commits, obviously. Pythonic is a C++ layer, so it's less than 50,000 lines of code of C++ code, and that's most of the code. There's a lot of tests too, because that's a hobby. So I don't want to spend time debugging because I have better thing to do. So if I have a lot of tests, then I can just write my code, launch the test suite, and it takes on GitHub 3 hours. On Travis 3 hours to run all the test suite. But then I can just go cooking, chopping wood or whatever, and then I go back, and okay, it works, and I can move to the other tasks. So that's not my work, it's a hobby. So having a lot of tests is a good way to have a hobby that can still be useful. And the Python code is actually very low. There is less than 20,000 lines of Python code to write this compiler. So maybe because lots of the part of the job is moved to the C++ stuff, but also because Python is a high-level language, so writing compiler in Python does not prove to be that difficult. So how does it work? You write your Python code, as you would do. You had these Python export lines. You learn the syntax of this single line. Then you call Python. It itself generates a C++ code that can be compiled with any decent C++ compiler, and it generates a native library that can be imported just like regular modules. That's part of the Python module import mechanism. But wait, it's not a translator. That looks like a translator from Python to C++ to native code, but that's not. Because recall, C++ is just a convenient backend. It's a very convenient backend, but it's just a backend. Python is a compiler. So you can view it as a source-to-source toolbox. You take your Python code, move to the abstract syntax tree, refine the syntax tree to optimize it for scientific computing, and then dump the result either as Python code, which makes debugging easier, or as C++ code. So there are three important pieces in Python: analysis, which try to gather information about the syntax tree; transformation and optimization, that both transform the code either to make it easier to analyze or to generate more optimized code. So that's just a bunch of keywords about the kind of compiler analysis we do. Use def chains, computing the effects of a function on memory, on arguments, on global memory. When you call a random function, there is a side effect on a state. So your function is not pure, so there are things that you can't do with your function, things that you can do. Sometimes you need to do a regular expression on the AST to replace an expression by a simpler one. Constant expression, which is basically equivalent to the context keyword in C++, but done without any keywords at Python level. Laziness analysis, computing that list comprehension could be transformed into a generator expression which avoids generating the whole list. Computing whether an expression is pure, does it have side effect or not. If it doesn't have side effects, then we can move it around. If it has no side effect and only constant parameters, then we can fold it at compile time. So you can write Fibonacci of 20, and Python will realize that Fibonacci is a pure function and just compute that at compile time and replace the result by the variation of this function. You can compute range for some values, stating that this variable is going to be between 0 and 20, and then maybe perform some optimization based on that. This kind of optimization we do is a generalization of loop unrolling, but for any iterator. So you can unroll a loop on a set, on a list, on a tuple, and that would work. Constant folding, but interprocedurally, thanks to the analysis I quote. Remove some modulo operation, which proved to be a very costly operation at the assembly level when it's done on induction variable. That's something people tend to do when doing image processing. Forward substitution to avoid temporaries, instruction combine to make some patterns appear. Simplify the code based on the range analysis, remove dead code. All this kind of stuff can be done at the Python level. And then you say, okay, he's basically implementing GCC, but at the Python level, what's the use? But GCC does not understand the semantic of a Python call. It doesn't know that numpy.ones has no side effects. So doing this kind of stuff at the Python level is just because once you're at the, say, LLVM level, at the bytecode level, you don't have this information anymore. So it's the right step. There is several layers of abstraction, and at the Python layer, you can do some optimization, and I don't do register allocation at that level because that's not my job. But wait, there are other compilers, and Numba, for example, expect your code to look like that. If it looks like that, there is loop, variable declaration, and then you can compile that to efficient code. But you can also write Fortran code that looks like that. We are in the 21st century. You can expect to write higher level code that still performs the same operation. Actually, this code can be rewritten in NumPy using that. And that's higher level. There is some temporaries that are generated because of the code to sum or because of the array expression at the end. But that's easier to maintain. And scientific people tend to write this kind of code. And then they say, okay, I want performance. And so, oh, I remember I used to write C. And they go back to this implementation. Even in Fortran, you can write this kind of code. So there is no reason why you should stick to that. So Python tries to compile this kind of code, which proves to be more difficult in a way, but that's why you need a compiler. Now, one of the most challenging kernel I had to handle was this one. It was on Stack Overflow, and the guy just pushed his code and said, okay, this is slow, how can I make it faster? And basically the answer was, okay, that's high-level code, write it at a lower level, make all the loops explicit, and there's still plenty of loops, and then you can call Siphon or number, and it will get faster. And that's true, it gets faster, and that's very pragmatic. I'm not stating that Siphon or number are bad compilers or whatever. They are very pragmatic and they work, which is something very useful. But still, we can dream a bit, and when it's not your work, you're allowed to dream. So Python tries to optimize this kind of code, and we can reach performance similar to number or Siphon on this code, while not writing all the loops. So that's what we try to do, but I'm relatively alone. There are a few power users, so some people did use Python to compile code that went into a small robot in the Baltic Sea. So there is Python code that runs under the sea, which is very cool. There is a firm in France, in Grenoble, that use Python for their daily task. Some academic work has been published using Python as an engine, not just as a subject of interest. And Martin did introduce some way to use Python in PX. And there is not a lot of developers, there is a lot of bug reporter, which is cool, because when your work is useful to someone, you're happy and you're more motivated to spend a few more hours during the night to improve your stuff. And some user suspects are very nice. And as it's a small community, you tend to learn people to exchange not about only code, but about any subjects. And I do appreciate that part of the open source life. But the road is very long. Supporting NumPy is a tremendous task. We're not supporting the whole NumPy API, even if we try to improve on that. Moving from supporting only Python 2 to supporting Python 2 and Python 3 was very difficult. Supporting OS X was okay. Supporting Windows is getting okay since last week, but it's still difficult, and it's only for Python 3 because Visual Studio for Python 2 is stuck to Visual Studio 2008, and it does not support C++11 at all. And so where would I find the motivation to go on that way, because it's not an easy way. So my opinion, when it's not your job, you have to find an interest. So either it's for fame, but that's not exactly the case, or because it's interesting as technical challenge. And one thing that deserves Python in a way, but also I find it fun, is you have to work to be good in optimization, low-level optimization, understand assembly when you try to debug vector SSE instruction. You learn a lot about the Python language because you're manipulating the AST, so you know stuff that exists in the syntax, and then you say, oh, I didn't know about that, and then you dive into the language, and you write a lot of modern C++, or C++ that tries to be modern, and there's a lot of stuff to learn that. So just for me, it's interesting to write this code because I learn a lot. But it's also interesting because I tend to meet other people, and the scientific community in Python is very friendly. The first time I went to SciPy, it was really, I used to go to academic conference, and it's not saying nothing that people in academic conference are less friendly than people in SciPy. It's just not the same kind of people. So I really love speaking with this kind of people, sharing ideas, and then you learn tricks on optimization, on benchmarking, and you just grow in knowledge and friendship with people that you would never have met otherwise. Even if your project is in a niche, there are still interesting people to meet, and that's very cool. The kind of thing you discover is, okay, Jupyter exists. 5 years ago, I didn't know about notebooks. And then I saw this conference, and I thought, okay, Python does it, so we should be able to have this Jupyter magic. And now there is a Python magic. You write your code, you call Python with your compiler flag, just the same as GCC flags, and it generates a native modules, import it into the kernels, and you can go on. You learn about capsule. A Python capsule is an opaque object around a native function or a native data, and it just provides a minimal interface for embedding a string and embedding a pointer, and it is used to pass data from native word to Python word back to the native word. Python can generate functions like here the foo function will accept a pointer and a pointer to a matrix, and it generates not a Python function that can be called at the Python level, but a capsule that embeds the native C++ functions hidden, generated by Python, and then you can pass this to SciPy as an optimization routine, and it works. So there is no Python glue anywhere, and SciPy native code calls Python generated native code without any overhead. And I didn't know about that, but Martin told me about that, and he said, oh, that would be cool. And because we generate pure native code that's easy to do in Python, implementing that took me two days because of the original design. And, well, that's just things I didn't know about in Python. You also discover that there is a standard to represent floating-point number, normalized, but NumPy doesn't care about it, which means that when you do complex numbers operation and the imaginary part is not a number, and you multiply this by infinity, what happens? Who cares? I don't, but the standard does, and NumPy people don't care either. And I discovered that because my code, my native code, was running slower than NumPy code, and I could not understand. I looked at the code, it was, okay, that's complex multiplication, and then I looked at the binary from NumPy, because, well, most of NumPy is written in C, and say, okay, that's not the same complex operation, and then you discover things. Because Python can generate vectorized code, not vectorized like vectorized array operation, but vectorized like using AVX or SSEs that are available in modern processor. I developed some more skills on that, mostly based on Boost SEMD, but also you learn to debug that. So that's just technical skills that happens to be funny. But wait, I also have a family. I'm the proud father of two lovely girls, so and I want to spend time with them. So there's two options. Either I teach them Python, and I try that, but that was not a success, or I don't spend that much time on my laptop and spend time with my children. So how do you find a balance between your regular work, which has nothing to do with Python or optimization, your family, your health, if you want to do sport or whatever, and open source? Either you sacrifice an element, which is a possibility, but from my side, I try to make sure that when I do open source, there's a benefit also for other items. When you gather more technical knowledge, then you're better at work. And for instance, tomorrow I will present something at FOSDEM related to my work, but as a side effect, they pay for my travel to come today. So that's cool. You can try to meet friends or family. I have a sister that lives in Brussels. I'm going to meet her tonight. That's cool. You can try to raise money, because when your wife is playing piano, if you develop, she's not very happy, but if you develop and you get money, then she's happy. So if you find a way to fund your work, then it's more legitimate to spend your time on your laptop. You may be an idealist and think that sharing knowledge is a good thing, and then just speaking in front of people or teaching scientific Python to researchers in France it's something you enjoy to do, and then you can do that. So I'm trying to mix everything. So Python is just a stone, maybe the keystone of that, but it enables a lot of things. And to my mind, it's a pet project. So it's not work. So at one time I was working with one of my former students, and we wanted to be very good engineers. So there was a very harsh review that was ongoing for every pull request, and we tried to write the best code ever. And after 6 months, motivation was gone, because when you wait 3 weeks and you refactor your code, and in the end it gets in, but it's 1 month later, it's not fun at all. You do that at work, and you're paid for that. But there is a balance between I want to produce things, and I want it to be correct, but not too much correct. It doesn't care. I don't care if I'm not supporting this sub-feature, because maybe someone will notice that there is an issue and raise an issue, and then I will redevelop. That way, it's okay to do that, because it's your free time. And we switched from this very harsh review to still review, but lighter review, and now it's healthier. And I don't have a Twitter account or trying to advertise a lot, just doing my pace, doing it at my pace. And some people tend to use it even if I'm not advertising that much. So as I'm not making a living on that, it's okay, and I'm probably happier like that. Happier, but I still want more. I have a funding to have Python being a piece of SciPy or a piece of Sage, which is a good thing for the project, because it's bigger kernels, so it meets the limits of Python. And I also get to meet a new community, and the SciPy community was very welcoming, and I really appreciated that. But they were also they also had a lot of requirements. They say, okay, why not Python? Probably not, but why not? But first you have to support OS X, Windows, and Linux. Okay. And then what is the size of the binaries you generate? Because we have requirements on that. Okay, C++, no, the size is going to be huge. And are there a lot of contributors? Okay, no, that's not the case. But till now, the binaries generated by Python are very slim, because there is, when you don't focus on a field, and then you, people tell you, please optimize that, there is a lot of low-hanging fruit. So I have a blog post. Later on you could click on that, and that explains how I made my binaries 10 times to 20 times smaller, just by using the compiler the right way, using C++ the right way. Windows support, as long as you stick to Python 3, it's not that difficult. Project maturity is going to be difficult, but times. Just to showcase or to express my feelings, 6 years ago I was hired at a company, and they wanted to start compiling Python project, but then I was leaving, and they told, okay, you're leaving, well, instead of doing that on our own, you can do that as an open source software, and we will pay you for that, because we already have a grant, and the job will be done, and that's okay. That was a very good idea, very nice from them. And then there is a European grant from OpenJunkit for improving Python, improving its use too. I regularly give teaching lessons about numeric Python in the group calcul from France, and I appreciate their help. And I try to be active in the French community on Linux FR. They are very friendly, and well, I just enjoy writing. It helps me make my mind more clear, and it also, some people tend to enjoy reading it, so it's okay. And sometimes very strange things, but very happened. I received that mail. So that was 2 years ago, and that was, okay, hi, you don't know me, I read your PhD thesis. When someone told you, I read your PhD thesis, that's strange, very strange. But they investigated my work and they say, the thing you've been doing in Pythran, it's nice. I think you have ideas that can be helpful to us. And then we worked together for 1 year. That's cool. I mean, that was completely unexpected. But just saying thank you was nice, but going that way was very nice. And last December, there was someone from Google Brain that just sent me an email saying, okay, we are using GAST, your Python 2, Python 3 layer, and it works, it just works. We're happy, thank you. And whoa, that's great. Really, that's the best thing you can expect. So that's my little story. Use Python if you like to, contribute to open source because it's fun, and if you have any question, we have 10 minutes or so.
Раз.
Okay, very nice talk, by the way. I really enjoy it. I would like to know, since you are using NumPy, do you rely on BLAS or LAPACK implementation, or is it pure C++ implementation?
No, we are not that mad. For all the dot operation, we are falling back to the BLAS. What we can do that NumPy can't do is the BLAS API is not only about matrix multiply. So we match patterns, and we say, okay, these patterns is implemented in BLAS, so we generate the right call. So and we just we can use BLAS or OpenBLAS as a backend. I never tried with MKL, but
that
I
was my
assume it should work.
question, by the way.
Yeah.
Okay, thank you.
Hi. Thanks for the great talk. I was wondering, how does Pythran compare to NumPy and Python in terms of performance?
So the question was, what about performance? I didn't show any benchmarks here because I want to make friends, not opponents. Basically, it depends. So first, NumPy is a JIT, so there is a JIT compilation time. It's cached, but it depends on the usage. So I will speak about Python, Cython, NumPy, and Pythran. There are a lot of kernels that Pythran supports that are not supported as is by NumPy or Cython because you have to expand the loop. And in that case, we generally match the NumPy performance. Cython is generally a goal, so we try to be as fast as Cython generated code while keeping a higher level input language or input, and without any annotations. Sometimes NumPy is faster, sometimes Cython is faster, sometimes Pythran is faster. One place where we shine is when you have, for instance, it was at the beginning, I can go back to that. This function, the Rosenbrock function, we are especially fast on that because we know how to generate AVX instruction for this kernel, and Cython relies on GCC or Clang to generate these instructions, but it's too late because of aliasing, or so it's not as efficient as manually generated patterns, because it's, from a compiler point of view, it's a difficult task. Less difficult now, but still difficult to generate good vectorized code. I know, but not for sure, that NumPy has a decorator to annotate ufuncs, but I'm pretty sure that they don't match Python performance for that kind of kernels. Then on some situation, for instance, for the Gray-Scott, For this kernel, Python is still slightly faster than Python, but there is a lot of work to match the lower level interface with that interface. Numba supports classes. Python does support classes, Python does not. Because in Fortran there is Tran like Fortran, and there is no class in Fortran, so that's legitimate. That's okay. And it's not a big deal, but some kernels I can't compare to them because we don't support the same input. So basically that's the idea. We all go the same way. The single thing Python has that the other don't have is native vector instruction support, and in some situation compiler optimization. I didn't speak about that that much, but I have a blog post on that. The modulo operation is not optimized by GCC or Clang, and if it's not optimized by Clang, it's not optimized by LLVM, in fact. And so neither Python nor Numba took advantage of the optimization we developed in Python. So in that specific case, we are faster because we have Python-specific optimization.
Thank you.
I have a question about dependencies in generated C++ code. What does GCC or Clang compiler depend on? You mentioned some algebra library, BLAS I suppose, and probably standard library. Is there something else you need to have to able to compile?
Currently, we depend on the standard library for all the random stuff. For instance, for vector implementation, we did not implement that. We depend on BLAS for the linear algebra, and that's all. And we depend on Boost SEMD for an abstraction layer for vector instruction, but it's shipped with Python, so you don't need to install it. If you're concerned about dependency when I install my code, then you just need modern C++ infrastructure, and that's okay, plus the BLAS, but you have them because you have NumPy installed, probably. I'm not 100% sure. And that's it.
I'd like to ask about, do you use SIMD instructions inside C++ code? Do you use intrinsics, compiler intrinsics?
Not intrinsics, because of Boost SEMD, which provides a target-independent abstraction layer. You manipulate vector data, and it just generates the right intrinsics depending on current platform.
How many
Not for all platforms, but x86 is okay.
And ARM, for example?
And ARM is probably okay, but not the latest instructions. I'm not 100% sure.
Okay, thank you.
Thanks, very interesting. I have a question about array operations and NumPy. So one of the performance killers when it comes to array operations is auto-creation of temporaries, where you just write arithmetics on arrays.
So if I understand correctly, the question is, when you have that kind of expression, that's a big array expression, the last one, the last assignment, in NumPy, when you do that, there is a temporary array that is created for each node in the expression, and that's a double source of slowdown. The first source is from memory locality perspective. It's not good because you're allocating new memory and writing to it, so the data are not in the cache because they are created to hold the new value, and it's also bad from loop pressure point of view, because there is a loop for that operation and a loop for this one and a loop for this one. So there is a lot of loops and not good memory locality. And the usual way to catch this pattern in C++ is to use expression templates, so that basically you delay the evaluation of the expression until its assignment, and that's what we do. So we have expression templates, and we also, but they are handling this kind of expression is relatively easy.
the Rosen one would be more tricky.
What?
The Rosen example would be more tricky.
No, the Rosen was relatively okay. This one is difficult because U and capital U and capital V are views on other array. Here, no, lowercase u and v are view on uppercase U and V. So you have an expression that creates a view, and then you use this view even just here, and you update the content of capital U through the view of smaller case u. And doing that using expression templates is tricky, but it's also a big way to learn that you have move semantics also for member functions in C++. There's a lot of things to learn when you want to optimize this. I'm not saying that's the beautifulest code I ever wrote, but it turns out to work, which is already a good thing. But that's a difficult part.
Thanks.
Okay, no other questions. So let me thank you again, and have a nice weekend.